Those of you who remember the first Shrek movie probably remember the layers scene. Shrek tries to explain to Donkey that ogres, like every other living creature, have layers, and they are not one-dimensional evil creatures. This is one of the funniest scenes in the movie, and it makes me laugh every time I watch it, and I watch it a lot. And it also holds true for software architecture, because a good software component, just like evil ogres, will always have layers. The role of the layers, though, is quite different in software than in monsters. The layers in software component represent the horizontal functionality of the code in the layers. Now, what does it mean? Traditionally, software components perform three basic actions. 1. Expose the software functionality through some kind of interface. This is usually done via API or user interface, depends on the type of the application. 2. Execute logic on the data that is received from the user, again via API or user interface. This logic often includes validation, processing, additional calculations, enrichment, and more. And 3. Save the data into the data store and retrieve data from the data store. Now, these three actions are usually represented as layers, when every layer has its own name. In software components architecture, these layers are called user interface or UI if the component has user interface, or service interface or SI if the component exposes API, business logic or BL, and data access layer or DAL. Each layer consists of various classes that handles the layer's designated task. For example, the DAL layer will have classes that handle opening connection to the data store, querying data, saving data, handling transactions, and more. The BL layer will have classes that performs validation, enrichment, and computations. The SI layer will have classes that exposes API, translate JSON documents to concrete objects, handle authentication and authorization, and more. Now, you might be asking, what is the purpose of the layer? Why would I want to separate the code to these layers? Well, there are some very good reasons for that. First, it forces you to write code that is well-formed and focused. It's generally a bad idea to write a method that performs multiple tasks, and we'll discuss it later in this section. And by splitting the code to well-defined layers, the code will deal only with its layer's goal. Second, layer component is a modular component. As you might recall, we discussed modularity as one of the most important quality attributes of a software, and by implementing layers, our component becomes just this, modular. Assuming the communication between the layers is done correctly, and we will touch on this in a minute, it's extremely easy to substitute layers. For example, if the current DAL implementation works against SQL Server and you want to switch to MongoDB, in a well-layered component you will only need to replace the DAL layer and no other layers will be affected, which makes your code really modular. In order to develop a good layered architecture, there are some concepts that must be followed. 1. Code flow, which means a layer can call only a layer that is directly beneath it in the code. What this means is that, for example, the code in the SI layer can call only a code in the BL layer, never a code in the DAL layer. In addition, a code can never call a code in a layer above it. For example, the DAL code will never call a code in the BL layer. The idea here is to keep the separation between the layers as strict as possible. If you will enable skipping layers, that will mean that the SI layer, for example, knows about the DAL layer. And that means that if you will change the DAL layer, it will necessarily affect the SI layer, making the whole component much less modular. Second, loose coupling. We will talk about this concept much more in the next lecture, but suffice to say that we need the layers to communicate with each other in a way that will have the minimum impact when there is a change. Let's see an example for this, which will explain this concept. Let's say this is the code in the BL layer that calls to the DAL. The specific code is written in .NET, but it holds true for any other language too. As you can see, the code references directly the DAL classes using the new keyword. Although easy to implement, having a direct reference between layers will render them strongly coupled. What this means is that if you will try to switch to other DAL, we'll have to touch all the code that references it from the BL, and that's bad. The correct way of referencing layers is via dependency injection, when the calling layer references only an interface representing the desired functionality, but not the concrete class in itself. Later, when we switch to other implementation, the BL code will not be affected since it wasn't referencing the DAL in the first place. This concept is called dependency injection, and we will discuss it later in this section. The third concept is exception handling between layers. Now, while the first two concepts are quite known, this one is more obscure and not all architects are familiar with it. The exception handling concept states that each layer must hide its inner exceptions and not let the layers above it to know about it, but rather let them add generic non-specific error message. For example, let's say our DAL works with MySQL database. Now, database exceptions tend to be very specific, which is good since it helps us pinpoint the problems and fix them. The problem is that this exception is thrown as a MySQL exception class, and it contains data about the inner workings of the database. One of the most important concepts of the layer architecture is that each layer is encapsulated and does not expose info about its inner workings. If the DAL will throw this exception, that means the BL will know the DAL is using MySQL, while it should be completely oblivious to its inner working. So the correct pattern here is for the DAL to analyze the exception, write it to a log, and create another exception called, for example, data exception, with a generic error message that there was a problem accessing the data store. This way, the only thing the BL knows is that the DAL has some problems with the data actions, which is fine, because that's all it has to know about the DAL. So these were the three concepts that make a good layered component. Now, there is an additional point I would like to cover. You might have heard about a concept called an n-tiered application or a three-tiered application and wondered what it is and what is the difference between tier and layer. Well, it looks like those terms tier and layer are often interchangeable, but they shouldn't, and there is actually a big difference between them. A layer is what we talked about, a piece of code that is part of a component. A component, let us all remind ourselves, is a code collection that runs in a single process. There is no networking involved when the various classes in the component communicate with each other, and they all share the same computing resource. Tier, on the other hand, is a distributed piece of code. It's deployed independently and communicates with other tiers via network protocols such as HTTP. So when talking about a three-tier application, what we actually mean is that the application has three independent components deployed across the network that communicate using the network, which is completely different from layers, which are part of the same process. Okay, so that concludes our discussion around layers. Keep in mind that layers are almost always a good idea, and it should be your default pattern for implementing components.